Section 27.7 is looking at the diffraction grating. So this is yet another application of diffraction. This is a special arrangement where we don't just have one opening, like our single slit diffraction, but we have a large number of closely spaced parallel slits. So notice instead of just having one, we now have, this is shown with 5, right? And they're very close together. They're all parallel to each other. It's known as the diffraction grating. And so what we get is that there's once again a bright spot in the middle. That's been very consistent, so that's nice. But we'll also have conditions to get to a maximum on either side, first order maximum, that's offset by some angle of theta. So let's take a closer look at this. So to get to the first order or the second order maximum, it's going to have to be with two adjacent openings separated by whatever separation distance d there is between the slits. We'll get a constructive interference if path length 2 is an extra wavelength longer. That matches our constructive interference condition, so that will be at some angle theta. Similarly, our second order maximum will be when the two slits right next to each other have a path length difference of exactly 2 wavelengths, 2 lambda. And so this is actually remarkably similar to our double slit setup. So let's compare. This is a plot of the light intensity, how bright the light is, as a function of the m value, right? So in the middle is the central fringe, the m equals 0, and then you have the bright fringes on either side. And it's shown for the grating, the diffraction grating that has multiple slits, as well as for the double slit, which only has 2 slits. And the thing to notice here, first off, is that the fringes produced in the diffraction grating are much narrower. There's a much smaller angle over which there's constructive interference, and it drops off fast otherwise. And there's 5 slits. When there's only 2 slits, it doesn't drop off as fast. So the bright fringe is wider. There's more of a region where it constructively interferes, at least a little bit. The other really interesting thing to notice here is that the peaks are in exactly the same place in the diffraction grating that has 5 slits and the double slit that only has 2. The m equals 0 matches, the m equals 1 matches, the m equals 2 matches. The only difference is that width of the peaks. So if you're just trying to find the maxima of the diffraction grating, these principal maxima, the very tall peaks, it follows the exact same equation as our double slit experiment. Sine of theta is equal to m times lambda divided by d, where d is the distance between adjacent slits. So that gives you some sense of it. There also are these secondary maxima. These are, we're not going to need to worry about that so much here, but it comes from the diffraction effects as well. But you can just focus on finding those principal maxima, the really tall and bright ones. So let's look at an example of this so we can see it in action. A mixture of violet light, wavelength 410 nanometers, and red 660 nanometer light falls on a grating that contains 1 times 10 to the 4 lines per centimeter. For each wavelength, find the angle that locates the first order maximum. Okay. So we ultimately, what are we solving for? Find the angle. So we want to find theta locates the first order maximum. First order gives us a clue to the m value. The picture also gives us a clue too. If it's first order, then that's not the central max, that's m equals 1. And that's going to be more interesting for this problem as well, because we know the central max will be the same for both of them. It'll be right in the middle, that's where we have the white light. But on the first order max, they'll be at different angles, which should be interesting to tell. Notice they also gave us our wavelength lambda for each case for violet and red, so that's great. Now, I want to take a closer look at this number, the 1.0 times 10 to the 4 lines per centimeter. What is that trying to say? Well, that's trying to show that, okay, we have a whole bunch of lines within 1 centimeter. But what we ultimately want to find is not the number of lines per centimeter. We want to know the distance between two of these lines, right? Because that will be our D. So what we're going to need is a way to go from number of lines per centimeter to just centimeters, right? Different value there. So paying attention to the units, if this is lines per centimeter, then I could flip it and get centimeters per line, right? And so to get to D, the distance between the lines, we actually just need the inverse of this. So if n is the 1.0 times 10 to the 4 lines per centimeter, we want the centimeters per line. So it would be 1 divided by, this would be 1 times 10 to the 4 is 10,000. Lines per centimeter. And so if we do that division out, then you should get that it is 1 times 10 to the minus 4 centimeters. So it's just flipped to a minus 4, but it is in centimeters. To get to meters, remember centi is 10 to the minus 2. So I'd have to write this as 1 times 10 to the minus 4 times 10 to the minus 2 meters. So it'd be 1 times 10 to the minus 6 meters. And that would then give us the distance between the slits as opposed to the number of slits per distance. So we've effectively divided out the number and just focused on that slit distance. So now we can see how that goes into solving it. So if we solve for our angle theta with our condition for diffraction, we take inverse sine of, notice the 1 isn't even in here because it's first order, so it'd be 1 times the wavelength of violet light divided by d, where d is this 1 times 10 to the minus 6 meters. For the wavelength of the violet light, 410 nano becomes 10 to the minus 9 meters. And if you calculate that out, you get 24 degrees. If you do the same with the red wavelength, it's a larger wavelength, so it's a larger angle of diffraction as well. The red bends farther than the violet, so it is 41 degrees. And this picture is helpful for illustrating that, but the math shows it as well, that a larger wavelength will bend or diffract to a larger angle. So this introduces diffraction. The last bits of the chapter take a look at some applications that we have. So one of them is 27.8, looking at compact discs or DVDs and the use of interference. So this same application principle for CDs or DVDs here, that the way that they work is the CD or the DVD has been built to, on the bottom side, there are a series of pits. And they're a pit in that they're lower, if you view it from on top, like where the printing is, so they really stick down in the pit, and in between is called the land. And there's a laser beam that's incident on the bottom side of the disc. And so it will periodically catch part of the pit and part of the land. And then there will be interference, because for the part of the beam that goes all the way to the land, it has an extra thickness to pass through of air or the plastic coating. So there's that extra 2T, which can cause a difference in interference. And that is how we can code in all the hip songs and movies onto a single disc. That information is coded in red using interference patterns. Diffraction can be brought into it too, though, with a fancier CD or DVD player, if you put a diffraction grating in between the laser beam and the disc, the diffraction grating, instead of producing one bright laser, can produce three for the price of one. What a deal. So the central one is still tracking on the pits in the land, but the first order maxima is on either side, and it's on the in-between. So it makes sure that there is no variation, and if there suddenly is a variation, then it will adjust to get back on track. So your fancy Walkman that had an anti-skip might have been involved with a diffraction grating, if you even know what a Walkman is. I don't even know at this point. Another awesome application, 27.9, X-ray diffraction. So we can study the crystal structure of atoms at the scale using X-rays, sending in X-ray light, which is a light wave, and seeing how it diffracts off of the surface, where there's constructive or destructive interference to understand the pattern. So this is NaCl, rock salt, and this structure, it can be shown with diffraction. If you look at a diffraction pattern here, it looks very different, but that's because it's a two-dimensional representation. You could then reconstruct, and scientists have, to get this simple cubic form. This is also what Rosalind Franklin did. She used X-ray diffraction to study DNA, and that's how she discovered that double helical structure. There's a really nice YouTube video linked here, taking a look at how she did that and how you could see that with diffraction. So I encourage you to check that out. But otherwise, that pulls us through the rest of chapter 27. Note there are some summary slides here at the end, looking at interference as a whole, the different types of interference we can have, as well as the different types of diffraction that we can have, and finally, thin film interference. So those are a great resource for you. I'm also happy to answer any questions. So please do reach out. Let me know what's working for you, what's not. I'd love to hear from you.